Thank you, everyone, for the invitation to speak here. It's very exciting to be speaking at another department in Cambridge. So as Chris said, I work in the stats lab, working with Professor Samworth on various topics in statistical methodology and theory. And so today I'm going to talk a little bit about some of my recent work on upgrading survival models with care. So this is some joint work with some wonderful collaborators. So Henry Reeve and Oliver Fung, both former members of Richard Samworth's group. Sam Lambert joined the project from the Department of Epidemiology here at Cambridge. He's an expert in polygenic risk scores. Pramod Mukherjee is in the biostatistics department at Yale, and Richard is at the statistics laboratory here in Cambridge. So I'd like to begin with a bit of a motivation for why we're considering this problem in the first place. So it is sort of an increasingly common problem in modern statistics, particularly in biostatistics, that there are some existing models that are very popular, that are well used out in the real world by practitioners, maybe have been quite well established for a few years, at least by now. So an example of such a model is the SCORE2 model, which is a survival model for predicting cardiovascular disease events. And it uses, it's a fairly simple sort of linear predictor model based on 4 covariates and a few interactions between them. This was originally trained and released back in 2021 on just under 700,000 individuals, with just over 30,000 of those actually developing cardiovascular disease at some point. So a fairly small proportion of these people experienced an event at some point in the 10-year study period. And so the question that we're wanting to ask is, suppose that we run some new experiments. Perhaps we're interested in investigating some new genetic markers, or perhaps some new social factors or other covariates that we expect to be useful when we incorporate them into a risk prediction model. It may well be the case that collecting this type of data is relatively expensive, particularly if it involves sort of running novel tests, looking for genetic markers or something like this. And so typically the sample size that's available to such a laboratory running a new experiment is probably going to be quite substantially less than the 600,000 that was available to run on SCORE2. And so, of course, one thing that you can do is you can just pretend that SCORE2 doesn't exist and you can fit a new model on your relatively small sample size. But you might imagine that perhaps this is throwing something away, really. You're not using the fact that we already have a pretty good baseline model that uses some quite simple features for predicting cardiovascular disease risk. And so our main question is, how should one upgrade a model like SCORE2 using a new data set? What is the best way to combine these two sources of information? And so sort of just to emphasize how available these models are, I mean, you really can just go online to a website and plug in your 4 covariates and see what your SCORE2 risk is. It really is something you can just go and do immediately. And something that we think is important here is that we really only have access to the existing model and not to the existing data that was used to fit that model. This is quite common for privacy reasons. There was a certain amount of access was required in order to fit this model, and you may not want to have to apply for that every single time you want to use their model or use the information that they have in their model. And so we're not assuming that we have access to the original data. We're just able to query those models. Okay, so what do people do at the moment in this kind of setting? So in fact, this is quite an easy question to answer because several papers have actually already been published exactly on this problem of updating the SCORE2 model in the last few years. So for example, people have studied adding measures of kidney disease, some new covariates there. Social status, such as educational status, can be quite predictive, as well as a few other sort of test results that have been published very recently in order to improve this type of estimation. And the way that this is often done is in a relatively straightforward manner, where sort of an external study will be done to try and estimate the parameter of interest, say, associated with a new covariate. And then that new covariate is plugged directly into the SCORE2 model. And maybe this is okay. It has been validated fairly successfully on some large data sets, but it relies on the rather strong assumption that when you import your parameter, that it works the same way with the new covariates as it did with the old ones. And of course, this may not be true if covariates are highly correlated, and if, in fact, even sometimes the effect can swap direction. So this is sort of generally not necessarily the most principled thing that one might be able to do. Sort of more broadly, in statistical methodology, there are also techniques such as prediction-powered inference, developed by John Ducci and his group. The idea there is that you have sort of a relatively small set of correctly labeled data, and then a much larger set of machine learning labeled data. So it's been labeled by some AI model, and you don't know if the labels are quite correct or not. And prediction-powered inference gives you a way of doing sort of valid statistical estimation and inference in that setting where you're not sure whether or not you can trust the artificial labels. Another related field is that of transfer learning, where you sort of want to transfer models that have been learned on one population into a new population of interest. Okay, so before getting into too many details, I want to give a very quick overview of our methodology and sort of explain what the ideas are. So just to repeat the setup, we were allowed to query a few existing prediction models, which I'm going to denote by F tilde. So this is score 2, you should think about. We also have access to a new data set, and we're going to assume, for simplicity, that this is statistically independent of the original model. So really, this should be a different data set. And we're going to combine these to construct an aggregated estimator. So throughout these slides, I'm going to try and use sort of yellow for the existing models and pink for the new ones, pink for the new data, and blue for the aggregated models. Okay, and so our procedure is as follows. So we take our new data, and we split this into a training set and a validation set, maybe 50-50 or some other ratio. And then we train a flexible family of models just using the new data. So the idea of this step is to try to get as much information as we can out of the new data, which might include your new covariate of interest. Maybe this includes your new genetic marker that you want to use. We then construct convex combinations between all of these sort of flexible kernel models that we fitted on the new data, and we construct convex combinations between that and the existing models. So we sort of regularize back towards the model that we know is already reasonably good. And finally, we can fit these two tuning parameters. So gamma is just a tuning parameter for the kernel. This is sort of a complexity parameter for a non-parametric estimator. And the parameter theta, which is the convex combination coefficient that tells you sort of how much of the new data you're using versus how much of the old models you're using. So maybe this diagram explains the same thing. So we take our data, we split it into training and validation on the left and right. We use the training data to fit the kernel models. We construct convex combinations, that's the blue region between the kernel models and the external existing models. And then we use the validation data to pick out the best looking point in that set, just using likelihood cross-validation. Okay, so for the rest of the talk, I want to really explain some of the details of this, what we can say about it theoretically, and then give some implementation details. So firstly, I'm going to describe the statistical model that we're looking at. So we're working on survival analysis, so I'll try to set that up. I'll then talk about these kernel estimators, exactly how you go about fitting these estimators F hat. And then I'll talk a little bit about the implementation details, so how you go about actually optimizing over this blue set, for example. Okay. Okay, so here's the statistical model that we're considering. This is a fairly standard time to event survival analysis model. So we're assuming that our data is 2n copies. This is just so we can have n for training and n for validation of data taking the form of this triple XTI. So here x is a covariate. These are the features that we want to use in order to predict someone's relative risk. We have some technical conditions on this, but essentially these are any reasonable covariates that you like. They could be real numbers, they could be vectors, they could be even binary or strings, anything that you can sort of compare with each other in a meaningful way. We're going to write TS for the survival or the event time. This is the time at which someone experiences a genuine cardiovascular event. So in the SCORE2 model, this is not necessarily cardiovascular death, but it's just a diagnosis of a cardiovascular disease event. We're also going to include censoring times. So this is quite important in studies where people might drop out or they might die for a different reason. And so, you want to record the fact that that individual is no longer in your study, but they didn't actually experience an event. What you do get to observe is the minimum between these two times, right? Either someone has an event and you stop observing them, or they drop out for another reason. And we're going to assume that that there's a sort of no confounding assumption here where the information in X gives you all the information about TS and TC. So we're just going to write I here for the censoring indicator. So I is 1 if that individual was censored rather than experiencing a real event. So based on this model, we can posit a statistical likelihood for this. And this is based on a non-parametric version of the classical proportional hazard model. So if you're familiar with, say, Cox's model, that looks exactly the same as this model here, where there's a sort of non-parametric, unspecified lambda 0 of t. This tells you sort of how the population risk changes over time. And then there's a part that depends only on x. So this is called a proportional hazards model because the relationship between t and x is sort of separable in this way. Our difference from the Cox model is that we're allowing the exponent there to be any function f0 of x subject to some assumptions, whereas in the Cox model, this would just be something like beta transposed x, would be a linear function of the covariates. So this allows us to do a somewhat more flexible modeling. It allows us to sort of target nonlinear relationships between the hazard rate and the covariate. So our aim is to estimate this relative risk function. We want to be able to tell an individual, based on your covariates, how many times more likely are you than, more or less likely are you than background to experience one of these events within a 10-year time frame. And so there's a bit of a sort of technical subtlety here, which is that this term f0 is actually only identifiable up to additive constants, right? If I take that equation and I add 1, say, to f0, as long as I then divide lambda 0 by e, I get exactly the same model. And so there's no way to learn this from data. This is just unidentifiable up to this censoring. And so to get around this, we're just going to impose this assumption that the expectation of f0 under the law of x is equal to 0. So in some sense, this f0 function is sort of centered at 0. This also makes it easier to interpret because when f0 is positive, that means you're sort of more likely than average to have an event, and vice versa. Okay, so having written down the model, we can write down the partial likelihood for this. So this is called a partial likelihood because we're not really interested in doing inference on lambda 0 here. We only want to do inference on f0, which is the relative risk. Estimating lambda 0 is actually, generally speaking, a much easier problem because you can estimate it from the background population. So here the interest is on the dependence on the covariates. So we write down a few of these stochastic processes. So the event process ni of t. This is 0 until person I experiences a true cardiovascular event, and then it's 1. This Ri of t, this is the at-risk process. This tells you whether or not individual I is sort of still in the study. So this is 1 until they either get censored or they have an event. And then we have this global risk process, which sort of tells you how much risk is present in the population at any one time. So it involves looking over the individuals who are currently in the study, that's the Ri of t, and then weighting them by their relative risk given by their covariates. So having defined these sort of auxiliary variables, we can write down the negative partial log likelihood of this model as follows. And so maybe you can convince yourself that this depends on the times only through their ordering. So it doesn't really matter when things happen, it just matters what order things happen in. This is sort of the point of separating out the dependence of time. This is because the only place that t appears in this expression is through ni of t, which only changes at the event times. It's similarly invariant under addition of constants to f. We already know this because the model was unidentifiable up to changing the constant. So of course, so is the partial log likelihood. And finally, the map that takes f to the negative partial log likelihood at f is a convex map. So this means this is going to have some important implications for conducting the optimization to actually solve for the maximum likelihood estimator. Okay, so in order to define the kernel estimators, I need to give a little bit of background on reproducing kernel Hilbert spaces. So this is possibly the most mathematical slide in the talk, so I wouldn't worry too much. But the idea here is really to propose a flexible class of estimators that we can apply on your new data set while making sort of minimal assumptions. So if you want to, you could do all of this just using the Cox model, for example, just taking linear predictors. In order to do that, you just have to use a linear kernel here. So, by a kernel function, I just mean any function that is symmetric and positive semi-definite in this sense. And so some very typical examples here are things like polynomial kernels. So using a polynomial kernel, you can see that you can show that this is equivalent to just doing regression or survival analysis with polynomial features, right? So instead of just using your features, you use the features and those things squared and their interactions, for example. If you want something more flexible than that, you can use something like a Sobolev kernel or a Gaussian kernel. And these correspond in some sense to sort of infinite dimensional feature maps that can capture sort of some more fine-grained properties of these functions. So yeah, so for example, on the right-hand side here, these are examples of Sobolev functions. So these are examples of some of the functions that you could use in your model. As you can see, they're not polynomials, they're not particularly nice functions, but they are some smooth family of functions that might make a reasonable model for what this relative risk function actually looks like. So now that we've defined this class of functions, this reproducing kernel Hilbert space of functions, we can use it in order to optimize over, in order to fit our model. So I'm going to write gamma to be a regularisation parameter. This is just sort of controlling the complexity of the model, making sure we don't overfit. And I'm going to write Pn for the empirical measure. So this is just 1/n sum of I f of xi. And so we already have our negative partial log likelihood ln. And so I'm going to write down this loss function. And so the idea of this loss function is I'll sort of look at each term in turn. The first term, of course, is telling you that the negative partial log likelihood on your data at your candidate function should be small. That means that the likelihood should be large. Means you should fit the data well. The second term is adding a penalty to the complexity of the function that you're proposing. So if you propose a very complex function, its Hilbert space norm, this H norm, is going to be very large. And that tells you that perhaps this isn't the most parsimonious model to be fitting. The reason that we subtract off this Pn of f inside is exactly for this identification reason again. We already know that the partial likelihood is invariant under adding constants to this function f, but the Hilbert space norm is not necessarily. So in order to make that also have the same property, we're going to subtract off a centering term inside this norm. Of course, I really want to subtract off the expectation of f, but I don't know that, so I replace it with its sample average. The final term is essentially there to enforce that the empirical measure on our fitted function is 0, and this provides strong convexity. So this gives us a stronger guarantee on the convexity of this function, and it is important for optimization. So again, this H norm sort of controls the complexity. When gamma is large, we care a lot about the complexity, and we're going to fit very simple models. When gamma is small, we're not so concerned about the complexity, and we can fit a complicated model that fits the data really well. And so through the few theoretical results that I want to give, we're going to assume correct specification. So in that setting, that means, right, this means that sort of the true population parameter lies in the model class that you have posited. And so here, this is just equivalent to saying that F0 is actually in this reproducing kernel Hilbert space. So there's a natural trade-off here again. If I use a very simple kernel, then maybe the model is easy to fit and nice and low dimensional, but then your assumption that F0 is in this space becomes much stronger. So this is sort of a modeling decision that the practitioner is going to have to make. Okay, so that's about fitting F hat. That's how to fit a model on your new data set. So sort of the main point really is, okay, so what do you do with these new models that you fitted in relation to the existing models like Score2 that you can go and read off from a paper somewhere. And so we propose this convex aggregation procedure. So we're writing big theta here for, this is just the simplex, just the set of sort of convex combinations. And we're going to essentially write down a mixture between our new estimator in pink and our existing external model in yellow. And so we're just going to take a linear combination of the two such that those linear coefficients all add up to 1. So we're taking somewhere in the convex hull spanned by these models. So this gives us quite a large family of estimators now, right? This is now indexed by both gamma, which is the regularization of the kernel, and also by theta, which is the convex combination parameter that tells you how much weight are we putting on the new data versus how much weight are we putting on the external. So we need to choose those parameters, and we propose to choose these jointly using the validation data. So right at the beginning, we split our data into two. Half of that we've already used to fit these kernel models. And now we're going to use the other half in order to find some good values for these parameters, gamma hat and gamma check, sorry, and theta check. So this is just by partial likelihood cross validation. So once we've got those sort of optimal choices, we just plug them back in. That gives us what we call the care estimator, which is given by this convex combination with sort of data-driven choices of these tuning parameters. Okay, so any questions on the methodology so far? Yes.
Why do you choose to use kernel estimator rather than spline estimator or neural network estimator or other non-parametric estimator to estimate F0?
Yeah, so this is a choice that we made, essentially. You absolutely can use other flexible choices here. The reproducing kernel approach is sort of nice because it covers also parametric settings as well as non-parametric ones. So if you use sort of polynomial kernels or low-dimensional kernels, then you can get back sort of more familiar parametric behavior. But if you use something like a Sobolev kernel, you can replicate that truly non-parametric behavior where you have an infinite dimensional Hilbert space. You definitely could also do this with splines. Part of the reason that we wanted to do this is actually, even without the data aggregation part of this work, the reproducing kernels for survival analysis is, as far as we know, also new, whereas splines have already been studied. But of course, yes, you could plug that in and use the same ideas. Neural networks you could also do. The theory would be much harder because you lose the convexity. So you generally only get local optima when you optimize over neural networks rather than global optima. But I'm sure they're also useful in practice.
Well, in this slide, I just want to get a better idea of what you're assuming about the external data compared to the actual. Are you assuming that those coefficients are fixed, or are you? What are you estimating the coefficients governing the internal data? Or what are you?
Yes. So yeah. So these thetas are going to be estimated using the validation data.
Yeah.
And so you can interpret these as so. So we can sort of pretend that big M is 1 for now, right? If there's only one external model that you're interested in, that means big M is equal to 1. And so in that case, there's only two terms on the right-hand side, right? There's an F hat, there's an F tilde. The F tilde is score 2. So if you also only have one theta, right? So in that case, if theta is 1, your model is just score 2. If theta is 0, your model is just your estimator fitted on the new data. And so this gives you sort of a smooth interpolation between these two extremes.
Fitted on the new data, but the new data are from a published model with coefficients where you don't know the.
Sorry, so the new data that's used to fit F hat is your data set, right, that you've generated in your lab.
Right.
The external one is F tilde. And of course, maybe to actually implement this model, you need to go to the paper and look up their coefficients, for example.
The coefficients are fixed according to the
Yes. So so F tilde doesn't really need to be random.
Yes.
It's just a model that exists in the world.
And the X could be different in each model, I guess.
Yes. So one of the important things that we need is you need to at least be able to evaluate the external model on your data. So, if you have new covariates, you're going to have to sort of interpolate those in the old data, right? If I want to use score 2 on my data, but my data includes some extra genomic information, I essentially ignore that when I plug it into the score 2 model. Right. So yes, the X's might be different, but you can just ignore the ones, the entries that you don't need. Yeah.
So
Sorry, good.
No,
Just a quick question about the two-stage process. So here it looks like you're optimizing your gamma and your theta, but doesn't your gamma determine what the optimal kernel was in the previous step?
Yes, so we actually do a joint fitting strategy. So you're completely correct. If there were computational concerns or something, you could do this in 2 stages. You first choose the best gamma and then choose the best theta. But really you sort of want to choose them both together, because it's not obvious that the best gamma on your data is also optimal in combination with the external model.
Yes.
And so
I think my question, so your F hat that you're bringing in,
yes.
because you've already generated, so are you doing all 3 parts together then? So you have your parameters of your F that themselves presumably depend on gamma through the penalisation.
Yes, it is essentially a joint. Well,
Yeah.
basically you fix gamma and theta, find the F hat, and then optimize over gamma and theta. But that is equivalent to optimizing all 3 simultaneously. Yes. Yeah. So this sounds quite expensive. I'll talk a little bit about the implementation.
Just the last thing to stop. When you say square 2, you mean the point estimates that define the model. You're not assuming you have confidence interval standard.
That's right. Well, this is purely predictive. So all you need is to be able to plug in a covariate and get a risk score out. It does need to be the relative risk. So, for example, if you go online and use score 2, it doesn't give you the relative risk. It gives you your estimated survival probability in the next 10 years, which is not quite the same thing. But yeah, you need to look up the
initial publications would usually include relative risk score. It might be an odds ratio, but it'd be a point estimate and a
That's right.
measure.
Yeah, so we only need the point estimate. Yeah, and typically they publish tables with the coefficients. So
would there be any use in having any value in having?
Quite possibly, yeah. I mean, sort of the hope is that the cross validation is able to essentially automatically choose the best thing. But yeah, you can certainly imagine, perhaps models that have more confidence should be upweighted in some sense in the convex combination. The hope is that should happen automatically. Well, I say hope. I mean, we prove that you find the best combination. But yeah, those sorts of heuristics could be very useful. Yeah.
So just to check that I understand correctly, so what is the target population here? Is it the
target population is the population that the new data set came from? Yeah, because otherwise the cross validation is not necessarily approximating the right loss. Yeah,
that's an interesting point actually, because your data on which you have the extra covariate may actually be more selected in some sense than the big data set.
That's right. Yeah, so if you've done a very selective trial, this may not be quite the right thing to do. I agree. Yeah.
I think the 2 pieces of information might conflict in that sense.
Yeah.
Yeah. Okay, great. So I just want to talk a little bit about the theory for this model. I just have a couple of results to present about sort of what guarantees you can say about this. So the first slide I have here is purely theory just for F hat, just for the kernel estimator on your new data set. So sort of in response to your earlier question, this is actually new as well, or even though it doesn't have anything to do with data aggregation. Okay, so I'm going to define this L2 norm just of a function just being the expectation of this function squared. This has a sort of nice interpretation in the survival analysis setting because this is essentially the L2 loss of the log relative hazard ratio. So you can do some integrals and this is the same thing. So that's why we're sort of giving our results in terms of this L2 norm. It does have some interpretability. And we're going to, so I'm going to write down these quantities nu r and er to be the eigenvalues and eigenfunctions of this kernel operator. This isn't super important. The only thing you need to know about is this quantity h gamma. So this quantity h gamma in some sense tells you about the complexity of the kernel. Typically, this is a quantity which blows up to infinity as gamma comes down to 0. So as you apply less and less regularization, your model explodes in complexity. As you add lots more regularization, this goes down to 0. And so this sort of captures how complex your model is. If you have a finite dimensional kernel, something like a polynomial kernel, actually this thing's bounded everywhere. So, and that sort of makes sense because you don't always have to regularize a parametric model. It doesn't generally explode in complexity. it might overfit, but not in a sort of catastrophic way. And so this is our main theorem for the reproducing kernel estimator. We have two terms in the L2 loss of our estimator f hat. One of them is sort of a stochastic standard deviation type term. This looks like 1/√n rates if you're in a parametric model, which isn't what you want. And if you're in a non-parametric model, then you get some slightly slower rate that depends on your choice of the regularization parameter gamma. The second term is then the bias. This is essentially the price you pay for choosing a non-zero regularization parameter. And I'll show on the next slide in some specific examples of sort of choosing the optimal value of gamma in order to balance these two terms and get sort of optimal rates of convergence. Okay, so here's just a couple of examples of what this looks like if you choose a particular kernel. So as I said with the polynomial kernel, no matter which regularization parameter you choose, actually h gamma is just bounded by a universal constant. So there's no way that this can overfit in some sense, at least not asymptotically. So as you would expect, choosing gamma anything less than 1/n gives you √n consistent estimator of f0 up to some constants. And again, this is under the quite strong assumption, right, that f0 must be in the space generated by the kernel that you're using. So that's the price you pay, is this assumption becomes f0 as a polynomial. This is clearly quite restrictive. The Sobolev kernel sits sort of at the other end of the spectrum. It's a much more complex kernel. Now you can see that as your regularization parameter comes down to 0, this explodes like 1/√gamma, which means that, you know, if you don't regularize at all, you have the potential to overfit quite badly. And so plugging this into the main theorem and balancing the gammas by choosing gamma as something like n to the minus 2/3, we get this rate of convergence of n to the minus 1/3. So it's a little bit slower than √n, as you expect. But in exchange for that, you get this much more general assumption that the only assumption on f0 you need is that its derivative is square integrable. And so this is just a sort of general smoothness condition rather than an explicit sort of structural characterization of what f0 should look like. Okay. So that's all I want to say about the kernel estimator. So we also have some theory, of course, for our main proposal, which is for the care procedure that aggregates this external models with the new data. So I'm going to, okay, so there's some technical setup here, right? I want to assume that my regularization parameters are bounded in some interval. And I'm going to assume that, so this assumption of gamma h gamma being bounded is making sure I don't overfit too badly. And then for some range of this parameter s, which controls sort of the sub-Gaussian behavior of this random variable, so we show that the L2 error between our cross-validated care procedure, right, this is with the parameter-driven choices of gamma and theta, is close in the sense of it's only some constant times 1/√n away from the best choice of the tuning parameters. So this means that as long as there exists a good estimator somewhere in that blue region that I showed before, this procedure will find it up to some √n consistent error. And so in particular, you're free to sort of choose specific points in that simplex, right? So you're better than the best point in the simplex, which means that you're better than any of its extreme points. And so in particular, the care estimator must be at least as good up to some constants as just the existing model and just your new model. So sort of, okay, maybe this isn't a very groundbreaking thing to say, but it's good to know that you're robust against these kind of things, right? If you fit a new estimator and it just doesn't work, your model will fall back on just using the existing model, and vice versa. If your new data is really good, your model will, the care estimator will say, actually, we don't need score 2 anymore. Our model's just better. And so in the simulations that I'll show and then the real data study, generally some strictly sort of interior point is chosen in the simplex. It's almost always worth having some amount of the existing model just to get some regularization back towards something that works. We also show in the paper that you can show some similar things under covariate shift. So maybe this is a little bit about what you were talking about with if the distribution is not quite the one you want to be targeting. This is a very mild form of transfer learning, right, where the distribution of the covariates is allowed to change. I think what you were talking about is the much harder instance of where, you know, the response actually depends on the selection mechanism. And there, of course, this is generally not going to do as well as you would want it to do. Okay, great. So I promised I would say a little bit about the computational side of this, actually fitting these estimators. As you pointed out, there's a lot of optimization that needs to be done. So I just want to talk a little bit about how you do this in practice. So to compute that kernel estimator, what we needed to do was solve this minimization problem over a potentially infinite dimensional space of functions, right? This doesn't look good to start with, but luckily there's basically some tricks. So I'm going to write k bar for sort of the average of the kernel evaluated on the data. And I'm going to write k tilde for the centered version of the kernel, so it's k minus k bar. This again sort of works well with the that identifiability issue where I want to make sure that certain things are mean zero. So there's a version of the representative theorem holds here. So if you've seen the classical representative theorem, which is usually stated for regression rather than survival analysis, it basically tells you that yes, you want to optimize over an infinite dimensional space, but actually you only need to optimize over an n-dimensional space, and that the function that you're looking for can be written as a linear combination of the kernels evaluated on the data points. So this is essentially a sort of kernel trick that lets you write this. And so we reduce the dimensionality from infinity down to n. And now this just becomes an optimization problem over this parameter beta I. So it still could be quite high dimensional, right? I mean, if there's hundreds of thousands of data points, this is still maybe not the best thing to do. But at least in theory, you can solve this over beta and Rn using any kind of gradient method, because this loss function is strongly convex. So any kind of gradient descent will be fine. We found in practice that the BFGS algorithm is very effective here because it estimates some kind of curvature structure as well. So that's for fitting f hat. For fitting the tuning parameters, we do the following. So what we do is we just firstly evaluate all of the kernel estimators for each gamma. And a useful thing to do here is initialize with warm starts. So basically, if your sort of grid of gamma values is dense enough, the solution for the next gamma value is not going to be very far away from the solution to the previous one. So what you do is you start with the largest gamma, because that's got the most regularization. It has this nice tight cone shape, sort of parabola. It's fast to optimize. And then you warm start from that point every time. And eventually you sort of converge to the right solution for each gamma. Then computing, evaluating the validation loss on each of your candidate functions. This is much simpler because all you need to do is evaluate the likelihood. You don't have to do any gradient descent here. And so we also just propose doing a grid search over theta. If you really wanted to, you could also do some kind of gradient search over the simplex as well. But we find that this isn't really necessary. So just a picture for what this looks like. The left-hand side, this is the negative partial log likelihood of the model. And it has this sort of valley shape. It's convex, but it doesn't depend on adding and subtracting constants. On the right-hand side is the loss function that we use that comes along with this Hilbert space norm penalty that makes it strongly convex. When gamma is big, you get this very nice sort of steep paraboloid that's easy to optimize over. As gamma decreases, this function sort of flattens out. But because you can warm start, you can sort of find the entire solution trajectory fairly quickly. Okay, maybe I don't need to talk too much about overview of proofs. Essentially, the ideas are providing some bounds on the sort of functional derivatives of the partial likelihood, along with these sort of strong convexity properties I mentioned before on the population versions. Then all you need to do is make sure that the population likelihood is close to the empirical likelihood with some high probability. So this bound that I've written in the sort of second to last bullet point, this is really saying that the difference between the true population likelihood and the empirical likelihood should be small when either the sample size is large, that makes sense, but also whenever you're already close to the right solution, it should also be small. And this sort of double effect means that you get the right rates of convergence. And finally, we have to provide some empirical process theory for the difference between the empirical measure and the population measure on sets that look like these sort of balls that are composed of a combination of the L2 norm and the Hilbert space norm. Okay. So here's a simulated data study that we did. We're trying to sort of model something relatively realistic here. So we have quite a simple data generating process. So we have a constant sort of background hazard function because this doesn't come into the partial likelihood at all. And we're going to assume that the centering times are also just uniform for simplicity. So F0, which is our relative hazard function, we're going to write down as this function of, it's a function of 10 variables, but it only depends on the first 5 of them. So this is modeling a sort of sparse function type of setting, which might be quite common in high-dimensional scenarios. And because this function F0 is not a polynomial, it's clearly some kind of sine function, we're going to model it using a Sobolev kernel, because if you used a polynomial kernel here, you already know that you're misspecified. So we're going to use a truly non-parametric kernel to fit this. So on the left, this is just the data. So the circles, so this is the estimated survival function against time. Sensitive events are given by circles, and the black line is just the classical Breslow estimator of the survival function. On the right-hand side, this is just showing how the likelihood, depends on the choice of the regularization parameter. So the dotted line here is the partial likelihood. And of course, as you overfit, the partial likelihood gets better and better and better. But the validation likelihood on an independent sample displays some global optimum somewhere in the middle, where you're correctly balancing the bias and variance of the model. So this is just the sort of illustration on 200 data points. So for sort of the analysis of the care procedure on this data set, what we do is we defined a sort of a mock-up of an external estimator. And similar to score 2, what we do here is we just take this to be the best linear approximation to the first 4 variables, right? So this model is deficient in 2 ways. Firstly, it's linear when we know the real function is actually some kind of sine function. And secondly, it only depends on 4 variables when we know that the real regression depends on 5. And so the plots above sort of show what happens here. So on the left, we're showing what happens to the cross-validated choice of the convex combination parameter theta. So remember, theta equals 1 means you're relying on the external model, and theta equals 0 means you're only using your new data. So sort of as you expect, as the sample size increases, you start leaning quite heavily on the external model. As you get more information, this parameter starts to come down towards 0 as you start to actually find the true function. So the black line with the blue confidence region is our cross-validated one. The gray one with the black dotted line is the oracle choice, which is if you were able to evaluate the cross-validation likelihood exactly, what would you do? So you see it's actually fairly close when the sample size becomes large enough. The right-hand side just gives the L2 performance. This is just the estimation error of actually estimating F0. And so, of course, the external estimator does not depend on the sample size, we just fix it. But as you get more data, the kernel estimator starts out actually quite bad because it just doesn't have enough data to fit such a flexible model. But as the sample size increases, the kernel estimator starts to do well. And more importantly, the aggregated care method does better than either of them for almost all of the sample sizes. So it's sort of correctly using the fact that we have this flexible estimator and then this sort of baseline estimator. And if you use them both together, you can do better than either of them. Okay, so finally, we applied this to the score 2 model that I've been sort of talking about as a motivation. And so we basically made 2 upgrades to the score 2 model. The first one is adding a few features to it. Firstly, there's this IMD feature, index of multiple deprivation. This is a sort of social deprivation score. And secondly, we have 2 PGS scores taken from SAM's polygenic risk score catalog, which are known to be associated with coronary artery disease and ischemic stroke. The second change that we make is we allow for nonlinear estimates of the hazard function rather than just using a Cox model, essentially. So our new data is taken from the UK Biobank, and we compare it with a version of the score 2 model that didn't use UK Biobank data to make sure that we satisfy our independence assumptions. And of course, we don't know F0, so measuring the performance of these models is not quite as simple as just plugging in the estimation error. We use the concordance index instead. This basically tells you out of how many pairs of people did you correctly predict who was going to get the event first. So this is sort of an ordering. It's a little bit like a permutation test statistic. So we're going to use a quadratic polynomial kernel here. This is not quite as flexible as something like a Sobolev kernel, but it does allow for a bit more flexibility than just using a linear kernel. This is just what the data set looks like. On the left, you have the survival function for females, and the right for males. We're going to fit this separately on the two different populations, which is what score 2 originally did. So just to keep the populations the same, is what we're doing. As you can see, sort of CVD incidence is about twice as high for males as it is for females. Okay, so here are the results here. So I tried to keep this the same. On the left, you have the dependence of the convex combination coefficient theta, and on the right is the performance. This time we're looking at concordance index, of higher is better, rather than lower being better. So the left-hand side, again, I've just put in 0 and 1, so you can see where the score 2 models are and where the pure new data model would be. And again, we see this generally decreasing behavior, but it seems like the score 2 model is only used at sort of relatively low weighting, implying that as our sample size gets big enough, our new model is actually finding some quite useful new structure in the data. Similarly, on the right-hand side, so of course the score 2 model doesn't depend on n, it just gives you a horizontal line. And as the sample size increases, the kernel estimator is able to use those extra features and possibly also the nonlinearity in the kernel to fit a better model. Especially once you get above sort of 20,000 samples in the new data. The blue line is the care method. As you can see, it does better than both of them, particularly in the female case. We think for the male case, the reason it's not helping that much is because the kernel estimator is already so much better than score 2 that the aggregation isn't really able to do very much with that. Yeah, so I guess I'll just say very quickly about fitting. So I mentioned before that when you use the representative theorem, you convert this infinite dimensional problem into an n-dimensional problem. That's nice for theory, and it's nice for sort of small simulated data sets, but when you have 50,000 samples, even this is still too big to fit. And so what we do is we go back to a sort of more classical setting, where instead of fitting in sort of the n-dimensional space, we fit in the d-dimensional space, where d is a number of covariates. So maybe you've seen this trick of the kernel trick, right, where you can essentially exchange sort of covariance matrices with gram matrices, and you can do the optimization in hyperspace. So just for disclaimer, we do this in sort of the easier case. This is why partly we don't use a Sobolev kernel here, is because using the Sobolev kernel does actually require you to do the n-dimensional optimization problem. It's possible that you could use ideas like random Fourier features to get around this kind of problem, but it's not something we looked into in this work. Good. Okay, I'm very happy to take any questions. Thank you.